Algebra 2, Chapter 7, Section 4, Modeling with Power Functions. So we're going to do some applications of power functions by trying to model data sets as power functions. First, let's practice. Find a formula for y in terms of x. A, the quantity y is proportional to the fourth power of x, and y is 150 when x is 2. So that tells us y must equal some constant times x to the fourth. Remember, that's proportionality was a shorthand for this. Now we can use these two values to write an equation to find k. 150 for y, 2 for x. We get 2 to the fourth, which is 16, times k, dividing by 16. 150 over 16 is a number that's not too far away from 10. You get a calculator or look up the answer, and we get 9.375 is k. Part B, the quantity y is inversely proportional to the cube of x, and y is 5 when x is 3. So y equals some constant k over x cubed. So we need to find k. So we have 5 is k over 3 cubed. 3 cubed is 27. Multiplying by 27 on both sides, we get 5 times 27 is k, which is 135. I'm sorry, we didn't quite answer the question. Did we find a formula for y in terms of x? Not find the constant of proportionality. So what we need to be doing is finding the formula. We needed to find k to do that, so the formula would be y is 9.375 times x to the fourth power. That's our model. That's our power function model for this data point and this power or exponent. So y here would be 135 divided by x cubed. That's our formula for part B. The period of a pendulum is the time it takes to make one full swing back and forth. So if you imagine a pendulum in a clock or any kind of pendulum, if it's suspended from a point, it's pulled back some distance and let go, and it swings back and forth. So the time it takes for it to swing back and all the way forth, in other words, the whole time, back and forth, that whole time is called the period, p, and is measured in seconds. It's proportional to the length, L, in feet of the pendulum. So this length to the center of mass of the weight, L. If a 3-foot pendulum, again that'll be measured from the pivot point to the center of mass of the weight, has a period of 1.924 seconds, find the constant of proportionality and write p as a function of L. So the pendulum period p as a function of L would be a constant, and it says proportional to the square root of its length. Constant times the square root. We know when the period is 1.924, the output of at an input of 3 feet, the output should be the 1.924 seconds. So that tells us k square root of 3 should be 1.924. So doing the math, we have k should be 1.924 for the square root of 3. we get a calculator. .924 divided by the square root of 3 is about 1.111. So our function f of L will be 1.111 square root of L. And the output of that function is the period P. Now once we've obtained a model like this, we can use the model and apply it in other situations. The length of Foucault's pendulum, built in 1851 in the Pantheon in Paris, is 220 feet. Find the period of Foucault's pendulum. So the period, remember, would be f of L was the period, and the rule was 1.111 times the square root of the length. The length was 220 feet, so the period would be 1.111 times the square root of 220 feet, or about 16.48 seconds. So that long pendulum takes 16.48 seconds to swing back and forth. So how can we decide whether or not a set of data is proportional to some power function? So let's think about the length and weight of a plaice, which is a type of fish. Is it proportional? Well, it's not. Let's see if it's directly proportional first. So if it's directly proportional, remember the change in y over the change in x should be constant. That would be the slope. So here we have a change in x of 1 unit each time. Each of these lengths is different by 1. So what is the change in y here? We have 363 and 332. 363 over minus 332 is 31. 391 minus 363. 28. 419 minus 391. 38. Sorry. 419 minus 391 is 28. 455 minus 419, 36. What did I type wrong? 450, that's right, 36. 363 and 332. Let's look at that again. 363, 332, 31. Let's make sure my table is correct here. 363, 391, 419. Okay, so definitely not, it's not directly proportional because these changes in y are different. So what about other proportionalities? Could it be that y is proportional to x squared? So if y is proportional to x squared, we have y as some constant times x squared. So if we take a y value and divide by the square of the x value, we should get something that's constant. Okay? And we could do this too with linear by just dividing by x instead of doing the change. So let's erase this for a minute here. Let's think about y over x squared. So using a calculator, 33.5 divided by 332 squared times itself is 0.000303 or 304. 0.000304. Let's do it for the next one. 34.5 over 363 squared. 0.000261. So it's not the same. It's changing. So that doesn't look like a good hypothesis. What if it's proportional to the cube of x? Then y over x cubed would have to be a constant. So we can find the y value over the x value cubed. 33.5 over 332 cubed is about 0.000000915. 34.5 divided by 363 cubed is not the same number, so no, that doesn't work. Okay, so what about, so it's kind of have to guess around, right? What if we had it being inversely proportional? What if y is inversely proportional to x? I'm sorry, the cube of the length. Oh, so we could go through that too, but this doesn't look inversely proportional because this is going up, right? As we go, it's going up. So let's think about the cube again. And I think there is an error in the table. I think let's not look at this value. Let's look at these other values and see what see if it's proportional to x cubed. So if we have y over x cubed, and let's write it oh, and I've been making a mistake this whole time. The y value is the thing on in the numerator. It won't matter because the ratio will be the same, but by putting the y value in the numerator instead of in the denominator, we'll get bigger numbers, which will be good for comparison purposes. So let's look at this again. So if we have the y value 363, oh, and it will be different because I was cubing the y value on accident instead of the x value. That's what was messing us up. So 363 divided by 34.5 cubed is 0.00884. .391 over 35.5 cubed is 0.00874. Let's erase that. 419 over 36.5 cubed is 0.00862. 455 over 37.5 cubed is 0.00863. So these are all very close to being the same. They are changing a little bit. Let's keep going. .500 over 38.5 cubed, 0.00876. And 538 over 39.5 cubed, 0.00873. .574 over 40.5 0.5 cubed, 0.00864. 623 over 41.5 cubed is 0.00871. So we see that the difference is small between these. This is representing a real-world problem. Let's just check this when I X'd out and see if it's correct or not. So let's try that one too. 332 and 33.5. 332 over 33.5 squared, cubed, is 00883. Yeah, so it fits in there just fine. So 883, 884, 874, 862, 863, 876, 873, 864, 871. Those are pretty close. So pretty close approximation for all these numbers is 0.0087. So we had some 8 sixes and some 8 eights. So we could say it's approximately proportional to the cube of x. So y is 0.0087 times x cubed. And we found that because we pulled the x cubed under the y here, so we could take the y value and divide by the x value cubed, and we saw that was a constant for all these, or roughly constant for all these data points. So we're able to show that a good proportional model would be being proportional to the cube. So the answer would be yes. Y is the weight. So the weight is roughly proportional to the length cubed. Okay, and we even have an equation to give us an approximation. If we step back and think about this logically, the length of a fish and the volume of a fish, the volume should be probably proportional to the cube of the length, because when we find volumes, we usually have width, depth, and height to consider. And the volume and the weight are probably very similar. So this makes sense that the weight would be proportional to the length cubed. So let's determine the power function for this table. Here we have x being increased by 1 each time, but the y value is going down. So if this is a power function, it's going to have to be an inverse power function. The proportionality would have to be inverse. So let's just see, think about this. If it's inverse, we'd have y is k over x, which means y times x should be a constant. So let's see if that's true. Is it inversely proportional to? So we have 1 times 21,600 is 21,600. 2 times 5,400 is 10,000. 3 times 2,472. So it's not inversely proportional to the first power. Let's try, what if it was inversely proportional to the second power? Then the y value times the square of the x value should be constant. 1 times 21,600 is 21,600. So y is 5,400. X squared, 21,600. 2,400 times x is 3 squared, 21,600. So we found it. It's inversely proportional to the square of x. So our power function would be y is 21,600 over x squared. So going back to our Alfa Romeo, thinking about the braking distance, Remember the braking distance equation. The braking distance was proportional to the velocity or the speed squared. So what happens to the braking distance if... So the braking distance was how long it took us to stop from the speed that the car was going. So the speed here is fast. When we finish braking, it's 0. But it takes some time to do that, and therefore we have to go some distance just based on this initial speed. That's why we have braking distance is proportional to the speed squared. So what happens to our braking distance if the speed is doubled? So if we double our speed, if we put in double the speed, what would happen to our braking distance? So maybe it would help to plug in an actual number. So if the speed were 20 miles an hour, we would get a braking distance of 0.036 20 squared, which would be 14.4 feet. If we had a speed of 40 miles an hour, let's clean this up a little bit here, 14.4 feet. If we had a speed of 40 miles an hour, the braking distance would be 57.6 feet. So it's more than double. We doubled the speed, but the braking distance more than doubled. Let's think about what factor it increased by. If we divide them, we can find the factor. 57.6 divided by 14.4 is a factor of 4. So what happened if the speed was doubled? Then the braking distance goes up by a factor of 4. Whenever you see or hear the word factor in mathematics, think multiplication. Factor of 4 means multiply by 4. If we triple it, so if we double it, the reason why doubling is a factor of 4 is if I put in 2v into this original equation instead of just v, I end up getting 0.036 times 2 squared is 4 times v squared, which is 4 times 0.036 v squared. And 0.036 v squared was the original braking distance. So if I double my input, or my speed, I get quadruple, or a factor of 4, times the braking distance. So if we triple the speed, we'll get 3 squared, a factor of 9 in the braking distance. So if we double, we get a braking distance that's quadrupled or multiplied by a factor of 4. If we triple velocity or speed, the braking distance d goes up by a factor of 9. So tripling squared is 9, factor of 9.